What's up, everybody? It's Miss Wesley here with my cone to talk to you a little bit more about conic sections. You knew this was coming. We covered circles. We covered ellipses. I know I'm not as good at this as perhaps Armand would be or Nick Figlioli, but today we want to picture that this cone has another cone upside down on top of it, and you're cross-sectioning it into a hyperbola with two kind of branches going off the sides. It's as if you take an ellipse and turn it inside out. So let's go to Conics Packet 1, page 25, and can we look at the hyperbolas notes for a second so we can go over some important stuff about those? Okay, so this is page 25 of the packet. You probably have already actually looked at this page and maybe perhaps taken some notes because you've been looking ahead at a little bit of hyperbolas material. But there's Winnie the Pooh and Piglet. Looks like they're doing something cute like catching butterflies. So it gets me in a good mood to talk about hyperbolas. I don't really need you to write anything down on this warm-up section. I want you to start copying things if you haven't already as you get to the bottom of the page, the definitions and the important facts about hyperbolas that are going to be on the next page. I'd just like to talk about this beginning part. It's nice to just use what we already know about functions from earlier in mathematics to be able to decide a little bit about what some of these features should look like of this graph. You should be able to look at this equation, and does it look like a hyperbola equation to you? Because it should, right? You've got an x squared term, you've got a y squared term in the equation, and they have opposite signs. So that is going to give you, it's not going to be an ellipse, it's not going to be a circle, it should be a hyperbola. There's a couple of things we could have talked about together, but again, I don't need you to write it. You can tell just by a glance at the equation that you'll have x-intercepts at plus or minus 3, and that perhaps you'd know there would be no y-intercepts. There's no way to solve this with real numbers with 0 plugged in for x. And if we were back in the beginning of pre-calc and discussing some symmetric properties of these equations, hyperbolas that we talk about possess some good types of line and point symmetry. Hyperbolas we talk about have x-axis and y-axis symmetry. You could change the sign of either variable and you'd get the same equation back. You couldn't switch x and y and get the same equation. It doesn't have x equals y symmetry, but it does have origin symmetry. You could change the signs of both variables and you'd have the same equation back. So even just knowing one point up in quadrant 1 on the hyperbola, you actually by symmetry know 3 other points. You could map that point over the other axes into the other quadrants. And you can translate these things too. This is where I would start writing stuff down just in case you haven't already. If you haven't already, we can just chat. How you define a hyperbola, a set of all points in a plane for which the absolute value of the difference of the distances from two fixed points, the two foci, is constant. Think back to an ellipse, right? In an ellipse, the foci were on the inside, and the sum of the distances from a point to those two focus points was constant. Here, we're talking about the difference between this length and that length being constant along the hyperbola to help generate that shape. And we're going to change the vocabulary a little bit too. I hope you can forgive me for that. With an ellipse, we talked about the major axis, possessing all the important points, the center, the vertices, the foci. Here we're going to call that the transverse axis with hyperbolas. Think of it as the major. And here you really do only have 2 vertices because the hyperbola is kind of just got those 2 branches there with the foci on the outside. Another huge difference that we'll discuss on the next page, and I'll say it a couple times, C is greater than A here. It's greater than B and it's greater than A. Since the foci have come to the outside of the shape, it is the greatest of those 3 letters. So who's ready for page 26? Let's see. If you haven't written anything down here yet, you got to now. And I say you should get a couple different pen colors ready too. If you want to pause this video and grab a couple different pen colors, we're going to start marking up the diagram with some asymptotes going straight through. Here you have a horizontally oriented and a vertically oriented hyperbola. So one of each type. And both of them have these slanted asymptotes that come right through the center. They come right through H comma K, and the hyperbola branches hug those asymptotes. Now think of what you know about Miss Wesley. You know, as annoying as it is, Miss Wesley is a lefty, which is kind of annoying here because I constantly, you've seen it in class, I'm notorious for covering up my writing with my hand. So I have to just give you the disclaimer now. I'm going to be covering up my writing. I'm trying not to. I'm working on it. But you have the ability, like I said, to pause the video if you need to. And please, if questions come up, you got to ask me questions too. So I'm going to switch colors and make a cool dotted line box here. And we spoke of this a little bit the other day. the box is going to just touch the vertices of the hyperbola and then come down and touch its corner points are going to be on those asymptotes. And if you've got room for it, I want to label A, B, and C on this picture. So you've got vertices here and here. Vertex, where can I put a V? Vertex and a vertex, right? You've got foci on the outsides. And just like we want to define each of these things, just like it was for an ellipse, A is going to be the distance from center to vertex. We are going to write that on the side in a second. And B isn't really pictured on this diagram. If you made another axis here, this is called the conjugate axis. Think of it as the minor. B is the distance from the center to the endpoint of the conjugate axis. So A and B, A doesn't necessarily have to be bigger or smaller than B. It depends on the problem. But C is always the biggest of the three. We've mentioned that already, that C is center to vertex. So I'm going to take advantage of this space down the right-hand side and just write some definitions here that I think would be good for you guys to keep in mind. This is, okay, so what do we have first? Transverse axis. And like I said, think of it as the major of the two axes. It is, what does it? It's the distance from one vertex to another vertex, right? So I'd say it connects the two vertices, connects the two vertices. What else? Its length, here's me covering up my writing, is 2a. Let me show you that. Its length is going to be double what a is. And then you've got the conjugate axis. Think of it as the minor of the two. Conjugate axis. It's funny how the word conjugate comes up in a language class and so often in a math class. Go figure. So this is going to be the minor of the two. It has a less cool sounding definition. I'm going to say that it is perpendicular to the transverse axis. Transverse axis. And its length, as you could guess, would be 2b. And here is an appropriate time for a Shakespeare joke to be or not to be. Guys, that is the question in this packet as well as in Shakespeare. A, B, and C. Let's label those underneath. So A, right? We've talked about A being the distance. I'll put D-I-S-T, distance from center to vertex. Whereas B is distance from, we'll say center, ooh, did not spell that right. How about center to endpoint, E-N-D-P-T, endpoint of conjugate axis. Does that sound okay? So center to endpoint of conjugate, just like we labeled it on your diagram. And C is distance from center to focus. So from center to focus. What I like about A, B, and C are A and C are the same exact thing that they were for ellipses. The definition did not change. It's just that C became the biggest of the three. And that's a good thing to note, that C is greater than A and C has to be greater than B, which leads us to the normal Pythagorean theorem. The foci lie on the transverse axis. And here's the Pythagorean theorem as we know and love it for hyperbolas, as opposed to how it was with ellipses. C squared is definitely going to equal A squared plus B squared. And that'll come in handy in word problems too. Some of this stuff is actually already printed in the diagrams above, but here's a recopy. If your center's at the origin, expect your two numerators just to be x squared and y squared, nothing with them. But a hyperbola is going to have a minus sign in between them. And actually, I've already written something I didn't want to write. Can you flip-flop those for the vertical orientation? So let me go back to this one so I'm not getting ahead of myself. It's still standard form equals 1, just like it did with an ellipse. And a squared goes with the positive of the two fractions. You can say a squared goes first as long as you keep that positive fraction first. You can't necessarily just pick out a from the two denominators like you did with an ellipse just by saying a has to be bigger than b, because it doesn't necessarily have to be bigger than b. It's got to go with the positive fraction, and if it goes with the x's, you know you're oriented sideways, like the picture that's above. Okay, so I should have flip-flopped the two numerators here. Let's say y squared goes with a squared for this version, minus because it's a hyperbola. How about x squared goes with b squared? over b squared equals 1, like that. And more often, you'll see a shifted version of this hyperbola. You'll see a translation where your center is now h comma k. So x minus h squared over a squared minus y minus k squared over b squared has got to equal 1 if it's oriented horizontally. For vertical orientation, just switch those numerators. I don't want to make the same mistake. So y minus k squared over a squared minus x minus h squared over b squared, equals 1. And you've got your standard form. Asymptotes, last but certainly not least. Do not be afraid of asymptotes. They are not hard to find, especially if you can find the equation of a line. And I want to use an example diagram in this little corner down here that is oriented horizontally. So I'm going to draw a hyperbola, just centered at the origin, open sideways, left to right. Not my prettiest hyperbola, but it'll have to do. Here is your dotted line box that we kind of drew above in the picture. I'm just freehanding that. And then here are your asymptotes that go straight through the corners. And what we're interested in is a quick way, a quick common sense way to find the equation of the asymptotes. Well, if I think equation of a line, two things come to mind. Point or slope intercept form probably comes to mind, y equals mx plus b, or the one that I love, point slope form, y minus y sub 1 equals the slope times x minus x sub 1. And you have an easy out here. You know that every asymptote of every hyperbola is going to cut through the center of that hyperbola. So h comma k is your automatic point that's going to be on that asymptote. So if I use point slope form, which you can leave this in point slope form, it'll be y minus k, leave a space for the slope, equals space, and then x minus h. The asymptote goes through h comma k. Now let's deal with the slope. We've got other letters for those things. I think rise over run. In this picture, I run A, right, to get to the vertex, and I rise B, right? B over A. I know that's hard to see, but that should be your slope, B over A. And then you say, Miss Wesley, but I want to be able to write both equations of both asymptotes. Well, that's no big deal because this line slopes down at the exact same ratio. So plus or minus out front will do the trick to account for both asymptotes going through the origin, or the center, I should say. If this thing is translated, that's fine too. If the hyperbola is oriented up and down vertically, you still have y minus k, and you still have x minus h. Your asymptotes are still going through h comma k, but if you're up and down, you're now, to get from the center to this point on the asymptote, you're rising A and you're running B. We've flipped the slope. So this version will have plus or minus A over B as the slope of its asymptote. All right, now to finish things off, general form. This should look familiar. Ax squared plus cy squared plus dx plus ey plus f equals 0. Why does that look familiar? Well, it's the same general form I gave you for circles and ellipses, but we've put restrictions on A and C. With an ellipse, do you recall, A and C don't have to be the same number, but they have to have the same sign. And the opposite is true for hyperbolas. For hyperbolas, A and C must have opposite signs. I'm going to say this in a cool way. I'm going to say AC, the product AC has to be less than 0. As long as their product is negative, you know you've got a hyperbola on your hands. And if you're wondering, Miss Wesley, why do you keep skipping B? Can you not use the actual alphabet the way that it's written? Remember that we've reserved B for the XY term. It causes a degenerate case in conic sections, and that we'll get to later. The conics in this packet aren't really going to have that term in them. Okay, signing off for now. We've done a lot of work. So if you can see that, I'm going to drink a little sip of my Dr. Pepper and be on my merry way. Hope you guys have a great day.